Hi everyone, so today we're going to talk about characterizing stars. So we went over this in class, but I wanted to make a video just in case people are absent or if you wanted to go back and hear it one more time. So again, some questions that we always start off with. So what is the nearest star other than the sun? Is the sun brighter than all the other stars, or is it just closer? What color are stars? Are brighter stars hotter? What are the sizes of stars? And are most stars isolated from other stars like our sun? So the first term that we're going to talk about is apparent magnitude. So apparent magnitude is the brightness that we see from Earth. So when we're looking out at Earth, we see stars. Obviously, our sun is going to be the brightest star that we see, and then other brightness from there. So stars that we see quite frequently in the star that are pretty bright to us, we have our stars in the Orion belt. We have labeled with their apparent magnitudes, so we can see Sirius here, Eridanus, Bellatrix, and other ones like that. So looking at some of the definitions here, so we give brightness of objects in the sky by their apparent magnitudes because that's how we see them visible to us. So stars visible with the naked eye have magnitudes between negative 1.44 and about plus 6. So we can see some of these here. Our sun is obviously going to be the brightest star to us because that's the sun, the star that is heating our planet here, and then we go down from there. So another thing that we're going to talk about with apparent magnitude is our inverse square law. So the further the distance from the Earth, the dimmer the star is going to look to us. So doubling the distance makes the star look 1/4 as bright as it actually is. So tripling the distance is going to decrease it by 9. So if we look at this, if we are looking at a star, the further out we go, we're going to see less and less brightness, as we can see here with that yellow color becoming less and less bright or apparent to us. So if we think about this in terms of a car, these headlights look a lot brighter to us than, say, these headlights. So the further and further we look away, that light is going to be able to disperse more and allow us to feel like that light is dimmer than it actually is. Something that we're going to do that is kind of not the opposite, but a little bit different is absolute magnitude. So the absolute magnitude is the actual brightness of the star rather than its appearance to us. So it tells us how bright the star really is, no matter how far away it is from Earth. So are the car lights actually dimming as the car look away? No, right? So it might look a lot brighter here, but its absolute magnitude is going to stay the same through all of these 3 pictures. It just looks dimmer to our eye, which is the apparent magnitude. So no, their actual brightness, our absolute magnitude, is the same no matter what. But their appearance to us, they look dimmer. Their apparent magnitude is just in the eye of the beholder. So it looks dimmer to us, but their absolute magnitude is going to remain the same. So just like this is a really good example. So we see star A is closer to our observer here. And star B, you can see, is a lot larger, a lot brighter. But what we see is that these stars look about the same brightness in the sky. And this is because star A is closer to us, so its apparent magnitude is going to be the same as star B that is a lot further away. So taking a look at our temperature and color, we've talked about this a lot with our stars. We know that the hottest stars are blue in color. Our medium color stars are yellow or orangey, and then our coolest stars are red. And we've also seen this before in our video that we saw. So when we're using these to define the stars, oh, be a fine girl or guy, kiss me. So we know these spectral classes, the definition of our colors for our star, go through different letters, which is why we have that acronym at the top. But our blue-violet stars are going to be our hottest stars, about 30,000 to 50,000 Kelvin. And then we move down from there. So we go from blue-violet to blue-white to white, yellow-white, yellow, orange, orange, and red-orange. And all of those, you can see the significant temperature decrease with that. And we also know that at these times, we're going to see different things happening with what we call spectral lines. So we can see ionized atoms, especially helium here. In our first one, our O spectral. Neutral helium and some hydrogen for our blue-white. Strong hydrogen with some metals. For our yellow stars, we see hydrogen, ionized metals. We see neutral and ionized metals, neutral metals, and then titanium and oxide for our lowest stars, for our spectral lines. And bringing back to our favorite diagram here. So remember, we can see spectral type on the bottom, that is our color. On the side, we see luminosity, so how bright that star is. We also see absolute magnitude. And then we see surface temperature. So as you can see, surface temperature and our spectral color correlate, and so do our luminosity and absolute magnitude. So we've talked a lot about these diagrams so far, but we're going to dig just a little bit deeper. So we know with our main sequence line that runs kind of down the middle of our diagram here, when we get higher, we're going to see our brighter stars as well as our larger stars. But we also see these stars as less lifetime that they have. So our larger stars are going to have a smaller lifetime than these smaller stars down here, which are less luminous. And then we've also talked about the movement in this diagram. So once these stars at their core start dissolving, using up all of that hydrogen, we're going to start moving to different areas within this diagram. So they might move to a giant, they might go straight to a supergiant, and towards the end of their life, you know that we are either going to move to a white dwarf down here, or we are going to move to that supernova, which either results in that neutron star or our black hole. So our HR diagram, our star brightness is plotted against our color and our temperature. Our brightness and spectral type are related, which we know. Main sequence stars are fusing hydrogen into helium, and they fall along that curvature right there. Our giants are very big, but sometimes not as hot. But again, since they are so large, they're luminous, so they're in the upper right. And then our white dwarfs may be really hot, but they're not very luminous because they're so small, and they are below. So if we want to put this in super, super basic terms, our sun is going to be kind of our central idea here. We know when we have really, really hot stars, and then when they are bright, we're going to see them in the upper left corner. When we have really bright stars, but they are cooler, like those red giants, we're going to see those in the upper right corner. When we have really hot stars like our white dwarfs, but they're not as bright, we're going to see them in our lower left corner. And then our last one, when we see our cooler stars and they're not very bright, we're going to see these in our bottom right corner. Another thing that we've been talking about, size is going to be really important. So our cooler stars, like our red giants, but have such an enormous size, are going to be really, really bright. So hotter stars are brighter than cooler stars of the same size. Bigger stars are brighter than smaller stars of the same temperature. So the brightest stars are the biggest and the hottest stars. So that's going to be our brightest star. And we can actually calculate this with a formula down here. So we know L is going to stand for our brightness or luminosity. We're going to, and that is going to equal the radius of the star squared by the temperature of the star to the 4th power. So again, taking a look, each dot is a main sequence star. Our dot's number is our solar masses, and compared to our sun, which is 1. And then mass, brightness, and temperature increases from the lower left to the lower right to the upper left. Sorry. So we know that our smallest stars are also going to be our coolest. So if we look at our temperature down here, they're also going to be our smallest. So remember, mass takes a big precedent. And from here, we're going to see increasing from the bottom left to our upper right. So just going to review again, how near is the closest star other than our sun. So the closest star to our sun is going to be Proxima Centauri. And that is about 40 trillion kilometers or 25 trillion miles away. And it takes light about 4 years to reach the Earth from there. So that you can tell that star is going to be out there, though it's going to be very dim in comparison to our sun. So how luminous is our sun compared to other stars? Our most luminous stars are millions and miles times brighter, but they are less luminous to us because they are so far away. What colors are the stars? We know that we have a wide range from red to blue or violet, and white is in that spectrum as well. So remember, oh, what a fine girl, kiss me. That's going to be our spectral numbers, but we're starting from blue or violet, moving all the way down to red. Are brighter stars hotter or dimmer than are dimmer? So we have many bright stars, such as red giants, that are very, very luminous, but not as hot. So that's going to make a difference here. So remember, we have to talk about size, and which is our mass, and we have to talk about temperature. So what sizes of stars? Our stars are ranging from 1,000 times the sun's diameter to 1 in 100th of the sun's diameter. So we have a huge, huge difference of how large our stars can actually be. And then are most stars isolated from other stars like our sun? No, we're going to see a lot of our stars found in large pairs or groups. Okay, so this is the end here. If you have any questions about stars, this would be a great time to ask them.